the set V of all vowels in English can be represented as what? V, so we are looking at this example, V equals a set of all X such, V equals a set of all X such that X is what? Is a vowel in what? In English alphabet. Such that what? X is what? Is a vowel in English alphabet. And then also with this example as well, the set O of all positive integers less than 10 is represented as O equals what? The set of all X such that X is an what? Odd positive integer less than 10. And then it can also be represented in what? In this way. Can also be represented what? In this way that has been ticked. And then also with regards to this one, we see that what? The set Q exponent P of all positive rational numbers can be written as what? As this, which is Q is the set of all real numbers such that X can be expressed what? As a fraction P over Q, where what? P and Q are what? Are positive integers. And so yes, and so we want to look at the number set. We want to look at the definition of all the number sets that we have. And so we take the very first one, which is what? Is n. So n has to do with what? Natural numbers. And with natural numbers, these are what? Counting numbers. These are counting numbers, and then they consist of what? So they consist of what? Of 1, 2, 3, 4, and then so on. And so we also want to look at the z. The z has to do with what? Integers. And with the integers is what? This set includes what? All whole numbers and then their negative counterparts. And so it consists of the negative numbers down to -1, 0, 1, 2, 3, and then so on. And then also with rational numbers are denoted with what? With Q. And then with this, they are numbers that can be what? Expressed as what? As a fraction. They are numbers that can be what? Expressed as a fraction, where P and Q are integers, and then Q is not what? 0. And so this includes what? All integers, since any integer can be what? Can be written as n over 1, as well as fractions like 1 over 2, -3 over 4, and decimals. Yes, and so on and so on. And so we also have what? Please, because of time, let's hold on with our questions. Let's write down our questions, and then I'll get your points, that I'll pause, and then I'll take our questions. And so with the irrational numbers, so having explained rational numbers, let's look at what irrational numbers are. So irrational numbers are numbers that cannot be what? Expressed as a fraction of what? Of 2 integers. Yes, so let's take note of this, that what? Irrational numbers are what? Are numbers that cannot be what? Expressed as what? As a fraction of 2 numbers. These are stuff that we are supposed to read, and so I just want to touch briefly on them so that as we progress, it we will be refreshed on them. And so yes. And so real numbers, the next one has to do with what? Real numbers. And so real numbers are what? So with real numbers, the set encompasses what? All rational and irrational numbers. With real numbers, I'm saying that with real numbers, what? The set encompasses what? All rational and what? Irrational numbers. So any number that can be plotted on a number line is what? Is a real number. And so we want to look at the last one, which has to do with the complex numbers. So these numbers extend what? So complex numbers would extend the real number system by including the imaginary unit of I. Okay, so so we've explained all these. So so the complex numbers has to do with a combination of what? A real and then an imaginary what? Number in the form of a plus bi, where a and then b are real numbers, and then the I is a solution of the equation x squared equal to what? -1. Right? Yeah. So this, I believe all these are stuffs that we have read and then we have knowledge of. And to moving on, the important number set. So want to look at the notation for intervals of what? Of real numbers. And so with the interval notation for real numbers, this notation provides what? A shorthand way to represent strategies, to represent ranges of what? Of real numbers. And then it is crucial for what? Expressing solutions to inequalities, domains of what? Of functions, and then what? Other mathematical concepts. And so we want to look at the examples that has been what? Has been captured. You want to explain these four of them here, these four intervals here. And so let's pay close attention to this. You see, with the first one, let's look at the brackets. Let's pay attention to the bracket very well. The opening bracket and then what? The closing brackets. These two, where the dots are, these two. Let's pay close attention to it. So these are what? Are closed interval. The first example is what? Is a closed interval. Why? Why is it a closed interval? This is because it includes what? All real numbers x that are what? Greater than or equal to what? Equal to a, and less than or equal to what? B. And with a square bracket, let's take note that what? The square bracket indicates that what? The endpoint a and then b are included in the interval. And when you check the square bracket, you could see that both of them are what? Are closed. Both of them what? Are closed. And so hence what? A closed what? Interval. And so with the example given here, we could see that what? A and then B. So with X, so we could see that A is what? Is less than or equal to X, and then less than or equal to what? B. And so it is within what? The range. So the element of, so with this, you could see that what? We are within the range of what? Of A and then B. And so hence it is what? It's a closed interval. And so let's look at the second one, which is what? A and then B once again. So let's look at the brackets here. This time around, the second bracket has changed as compared to the first one. And so with this one, it is called what? Right open interval. And so this is because it includes all real numbers x that are what? Greater than or equal to a. So all real what? All real numbers x that are what? That are less than or equal to what? X, and strictly less than what? Strictly less than what? B. Strictly less than what? B. And then with the third one, with a third example, we see that what with a third example, it is called what? Left open interval. Left open interval. And then with this includes what? All real numbers x that are less than what? A, that are what? Less than A, and less than or equal to what? B. That are less than A, and then what? Less than or equal to what? B. Sorry, that are what? Greater than what? A, and then what? Less than or equal to B. And to the parentheses that was used here indicate that what? A is excluded, while what? The square bracket indicates that what? B is included. Yes. And then with the very last one here, it is what? Open interval. It is termed as what? Open interval. This is because it includes what? All real numbers x that are greater than A, and then what? Less than what? B. So x is what? Is greater than A, and then what? Less than what? B. And then less than B. And then yes. So with this aspect as well, we see so with this aspect as well, we see that what the examples here, with examples here, we see that what with examples this and then this, the underlined ones, we see or illustrate that what the set can have what other set as what their elements, and this is what foundational what fundamental concept in what in set theory. Please let's hold on with the questions. Like I said, I'll pause at a point and then we can ask our questions. So let's put down our questions. Yes, so continuing. So with the very first example, which is the N, Z, Q, and then R, this is a set that contains what? A set of what? Natural numbers, a set of integers, and then a set of what? Rational numbers, and a set of real numbers. And then each of these items within the outer set of curly braces is itself what? A set. And then with a second one, which has to do with the A, E, I, 0, and then 1. This set contains what? The letters A, E, and I, and then also contains what? The set that contains what? The numbers 0 and then 1, just as seen here. And so with this one, two sets are what? Just as seen here. So now with the equality of sets, we can see that what two sets are considered equal if they contain exactly the same element. Two sets are considered what? Equal if they contain what? Exactly the same what? Element. And so the order in which elements are listed does not it is not really important. The order in this scenario there, or in this in this sense, the order is not really what important. And so we see example here that 1, 2, 3 is the same as what? A set containing 1, 2, 3, and 5 is the same as what? A set containing what? 5 and then 1. And so if one of the set contain an element that the other set does not contain, then we say that what? The set is not what? Is not equal. They are equal if and only if both sides are what? Contains what? The same element. All right. And so looking at empty sets, we all know that an empty set is what? Is a set with no element. An empty set is what? Is a set with no element. And then an empty set can also be termed as what? A null set. A null set. And then it is often denoted by either this or this. Either this symbol, the null symbol, or this symbol as well. Yeah. And one thing you must know is that when you're denoting an empty set and then you go in this manner, so just this is an empty set, but when you go in this manner, when you go in this manner, one thing you must know is that this is not an empty set because it contains what? It contains an element. And so I remember one prof was teaching you guys in class, he made reference to the fact that when on your computer, when you have a folder named A, and then you create another folder inside that folder A with the name B, that folder A, though the folder B is empty, but because folder B is an element within folder A, it is not what it is not an empty set, but it now becomes what? A single set, as a singleton set, because it is having what? An empty set as what? As a member. But when you have a folder named on your laptop as C, which does not have any element, which does not have any another empty folder, then that is what is a complete what? Empty folder. And so that is what an empty set. And so we want to look at the Venn diagrams. So with a Venn diagrams are used to what? Represent the set graphically and to indicate the relationship what between two or more sets. And then in Venn diagrams, we see that what the universal set U is mostly denoted by what? By U. All the time you see our universal set denoted by what? By U. It contains what? All the objects under consideration. And then it is mostly represented by what? A triangle. And then the circles on the other hand, the circles on the other hand are used to represent what? The set. I used to represent what? The set. And so we could see the circle here representing what? The set of vowels. And then our universal set here representing what? The set of English alphabet. All right. So now let's look at subset. So the set A. So when we say A is a subset of B, A is a what? A subset of B, which is denoted as this. A is what? A subset of B. What we mean is that what the set A is what? Is a subset of B if and only if every element of A is also an element of B. And so this is this means that what if you pick any element from set A, that element must also be found within what? Set B. And even if one element of A is not in B, then A is not a subset of B. And so what I'm trying to say is that what when you say A is what? A subset of B, when you pick any element of from set A, that element must also be what? Identified or found in what? In set B. And so B then is and so like I was saying, if we happen to find an element of A which is not in B, it then mean that what A is no longer what? A subset of B. Okay, so like I was saying, when we say A is a subset of B, it is denoted by what? By this by what I've just circled here. And so once again, with okay, so let's look at this as well. So A is what? A subset of B if and only if the quantification for all x if x is what? An element of A, then x is also an element of B. For all x, if what? X is an element of A, then what? X is also what? An element of B. And so what this means is that what with this, with the underlying aspect, this means that what X is an element of A, and then with this also means what? X is also what? An element of B. And so this basically also implies that what? It's the same as saying that what every element of A is also an element of B, which is the definition of the subset that we've been talking about. So for every element of A is also what? An element of what? Of B. That is what we simply mean by what? By A is what? A subset of B. And so let's look at this example here. And so with the first example here, 1, 2, 3, 5, 7, we are saying that let's assume, so with this set, let's name this set as A, and then this set as what? As B. So with a set A, you see 1, 2, 3, 5, 7, 9 is a subset of set B, because we see all elements of what? Of set A, which is 1 here. We see 2 is also here. 3 can also be found here. We see 5 can also be found, and then we see 7, which can also be found here, and then we see 9, and then 9 can also be what? Be found here. And so with this, we can clearly say that what? Because we see all elements of set A in set B, we can clearly see that what? Set A is what? Is a subset of what? Of set B. Okay, so let's look at a proper set. Let's look at a proper set. So okay, so A is a what? A subset of B, but A is not equal to B. But A is not equal to B. What this means is that all elements of A are also in what? In B, but B contains at least one element that is not in A. In other words, A, every element of A can be found in B, but not all elements of B can what? Can be found in A. And so in such case, A is said to be what? A proper subset of what? Of B. A is said to be what? A proper subset of B. And so yes, and so let's look at this example. So A is what? Is a proper subset of B if and only if for all x, x is what? Is what? Is an element of B. Hello. Yes. So I was saying that yeah, with this example, so A is a proper subset of what? Of B, if and only if for all x, if x is in what? Is in A, then x is also in what? Is in B. That is when we can say that what x is what? That is when we can say that A is what? A proper subset of what? Of B. So with this part, so like I was saying, A is what is a subset of B if and only if what for all x is an element of of A, then x is what also an element of what of B, and what and with this one, what this implies is that what there exists what an x such that x is in B and x is not in what in A, which means that what B has at least one element that is not in what in A, and so together we can say what A is what is a subset of B, and B what has extra elements in this sense. So okay, so think let me pause here and then take some two questions and then we move on. Okay, Ebenezer, can you speak?
Hello, sir, Kingsley. Hello, sir.
Yes, please, I can hear you. Go on.
There was this statement I didn't understand because I was having a network interruption. It says that every empty set is a subset of every set. That statement. Empty set is a subset of every set. That statement. Can you please help me understand it?
Come again. What are you saying? Come again.
There was this statement before this. You see, after this slides, there was a slide before this. It says
Before this slide.
Empty set.
What's
Yes.
this page?
The last one. Yes, the last one.
This one.
Empty set. Yes, down there. Empty set is a subset of every set.
Ah, okay. You said you need explanation to this statement.
Yes, please.
Okay. Okay, so with this statement, what it means is that so with this statement, what it means is that let's look at some examples. So let's say set A is a subset of is a set. Okay. So yes. So with this statement, every set is a subset of every empty set is what is a subset of every set. That means for a set A, the null set is what is a subset of A. And so what this presupposes is that let's look at it in this scenario. So let's say a set A is what is a subset of a set B, which is written as what A is what is a subset of B if every element of A is also what an element of B. And so what we are implying is that for every element in X, for every element X in A, X is also in B. And so what is this empty set that we are looking at here? So the empty set, which is written as, which is denoted as this, is a set that contains no element at all. No element at all. So why is it a subset of every set? So for a null set to be for null set to be what? For every empty set to be a subset of any set we come across to be true, then every element of that null set must also and to because it has no element, it's because it has no element, there's actually nothing to contradict it. And so let's say every element of a null set is in A, which is true because there are no elements that could possibly violate it. That is why we mostly say that every empty set is a subset of what? Of every set. Because the actual reason is because there are no possible element, or there are no possible elements in that particular empty set that could violate this statement here. And so that is why it was captured in that manner.
Okay, so I clearly get you. Thank you. Yeah,
Okay,
I think
you're
it's clear
welcome.
for me now.
Okay, sure. So we want to move on. Want to move on to the the size of what? Of a set. Want to move on to the size of a set. Okay, so with regards to the size of a set, the size of a set is what? Is simply the number of distinct elements in a particular element. And so mostly what we denote the size of an element to be is what? Is like the size, what we can also call the size of an element is what? Is cardinality, which is denoted as this, as here the card. So the size or cardinality of an S of a set S is denoted as this. So cardinality essentially tells us how many distinct elements are particularly in a set, in a particular set. That is what that means. And so let's look at the finite set and then infinite set. And so if the number of elements in a set are finite and hence the cardinality of it can be determined, it is called what? Finite set. Otherwise, it is what? And then the otherwise or the vice versa will become what? Infinite set. I take it again. So if, like I was saying, if the number of elements in a set are finite and hence the cardinality of it can be determined, then we term that one as what? As a finite set. But the vice versa of it is what? Is determined as what? The infinite set. And so simply put, a finite set is what? Is a set with a countable number of elements. Is what? Is a set with what? A countable number of what? Of elements, of which we can assign what? A specific number to its cardinality. But infinite set has to do with what? An uncountable number of what? Has to do with a set with uncountable what? Number of what? Of elements. And so with this one, we cannot specifically what? Assign a specific number to its cardinality. And so we want to look at an example. So let's say, let A be the set of what? Of positive odd numbers. Let A be the what? The set of positive odd numbers less than 10. Less than 10. And so we all know that less than 10, we all know that what the positive odd numbers, the positive odd integers numbers less than 10, we have 1, we have 3, we have 5, we have 7, and then we have what? We have 9. We have 9. And when we want to find what the cardinality of the set of odd positive numbers, positive integers, the set of odd positive integers numbers less than 10, and we have 1, 3, 5, and 7, and we want to find the cardinality. Since we know that it is 1, 2, 3, 4, 5, when you count these numbers, the odd numbers which are 1, 3, 5, and 7 and 9, we get what? 5. And so 5 becomes what? The cardinality of what? Of the set A of what? Odd positive integers less than 10. And so when we also look at the second example, it says let S be the set of letters in the English alphabet. And when we count the English alphabet, we have 26 of them. And so the cardinality of S is what? Is basically 26, because the English alphabet is numbered at what? 26. And when we want to find the cardinality of what? Of an empty set, or of a null set, it is, simply put, it is 0, because it has what? No no element, and so it is what? It is 0. But the set of positive integers are infinite, because it goes on and on and on and on and on. Okay, so Aaron,
Please. Someone said explain the previous slides before the slide of the slides.
come again.
Someone said explain the previous slides before the size of a set.
I've already spoken about this. We've already dealt with the proper subset. So we are moving on. So we are moving on. I want to look at the power set. I want to look at the power set. Sorry, I'm coming. Okay, so yeah, someone is asking from that is a nice question here. Someone is asking in the chat section that what is the cardinality of a singleton set? What is what the cardinality of a singleton what set? And so with this, I want to ask the class, what could possibly be the answer? I've written it on the screen here. What could possibly be the answer?
Yeah, I'll say it's 1.
You say it's 1, exactly. Why is it 1? Because it contains what? It contains an element, right? Yes, so it is 1 because yes, it contains just an element, which is what the noun set. So yes, we've answered this question. So I want to look at the power set. So the power set of a set S is a set of all subset of the set S, which is denoted as what? P the bracket what? S. So example, we want to look at example. So when we have the set P, what is, when we have the set 0, 1, the element of the power set is as what? 0, 1, 2, 0, 1, and then 2. It is it is denoted as what? First of all, we have our null set 0, 1, 2, and then we now come to combine them. So 0 and then 1, 0 and then the 2. Then we are done with the 0. We are done mapping the 0 with all the other elements. So we now come 1 and then 2, and then we now come and map what 1 and then 2. When we are done, then we bring all of them together, which is we now bring 0, 1, 2, 0, 1, and then 2. Yes. So with this, with a second example, the power set of the now set here is just this. It's just this because it just has one element, and so we just begin with just that. And then we also have a singleton set here. The power set of what? Of a singleton set. And like I said initially, it contains what? An element. Let's not forget, it contains what? An element. And so we first of all bring the null set, and then the set of what? Of that null set once again. All right. So we want to look at the ordered tuple. Tuple. So with the ordered tuple, so the ordered n tuple is the ordered what? Collection that has what? A to the base 1 as its first element, and then A to the base 2 as its second element, and then A to the base n as its nth what? Element. And so this defines what? A sequence of n element where the order of element is crucial. And so n tuple simply means what? A sequence of what? Of n elements. Yeah, so n tuple means what? A sequence of what? Of n elements. And so for example, a 3 tuple would be, let's look at a 3 tuple. A 3 tuple would be into bracket what? A, B, C. Element of, just have a 3 tuple would be what? A set with what? With element of what? A, B, and then C. And then one thing you must know is that the order is very important. The order in order tuple is what? Is very important. And so looking at two tuples, we have what? A and then B. And then we also have what? A and then C. But we are saying that A and B, A, B, and C and D are equal if and only if A is equal to C and then what? B is equal to D. And then also with regards to this, you see a set containing elements A and B, which is not equal to B and B because the order is different. And so it will only be equal if and only if what? A is equal to what? B. If and only if what? A is equal to what? B. And so looking at this example, this last example here as well, for example, the ordered pair 1 and 2 is not equal to the ordered pair 2 and then 1 because there has been an interchange in what? In the order in which it appears. And so looking at the Cartesian product, okay, so even before we come back to the Cartesian product, okay. Yeah, okay, so yeah, basically that should be it for so looking at this once again, the last example here once again, it's actually the reason why it's not equal, it highlights what? The importance of order. And so swapping the element creates a different what? Ordered pair, unless what? The elements are identical. Unless what? The elements are identical, that is when it will not affect it that much. And so for example, looking at this same example again, 1 and 2 is not equal to the ordered pair 2 and 1 because it provides, because the first pair represents what? A point X. So let's say we are on a graph, and so the first point what? Represent X is equal to 1 and Y equal to 2 on a graph. But the second pair will represent the fact that X is equal to 2 and Y is equal to 1. That is why we are establishing the fact that this 1 and 2 here is not the same as what? 2 and then 1. All right. And so now let's look at the Cartesian product. The Cartesian product. So with the Cartesian product. So the Cartesian product of two sets A and B, denoted by A and B, is a set of all pairs. Is a set of what? All pairs AB, where A is an element of the set A, and then B is an element of what? Of the set B. And this means that you take each element. This means that you take each element from what? Set A, and then pair it with what? Each element from B, forming what? Ordered pair. Forming an ordered pair. And so let's look at this example that we have here. This example that we have here. And so we have what? The set A, which has element 1 and then 2. And then the set B, which has what? Element A, B, C. And so just as I was saying that we are to pair what? We are to pair each element of A with what? Each element of what? Of set B, so that we can form an ordered pair. And so we'll begin with what? With a 1. The first element of A, of the set A, which is 1. So we'll begin by pairing this one with all the others of what? Of the set B. So we'll pick the 1 and then we'll pair it with what? With the A here. And we'll come and pick the 1 again, still on the 1, we come and pair it with the B, which is seen here. And then we'll come and pair it with the last element, which is C, also seen here. And then we now move on to the second element of what? Of the set A, which is 2. So now 2 is paired with A, and then 2 is also paired with what? Is B. And then it's also paired with what? With the element C here as well. All right, and so each element of what? Of A, and if each element of A, which is 1 and then 2, has been what? Paired with each element of B, which is what? A, B, and then C. And when you look at the second example which was given here, which is talking about students and then courses, we see that what? A and B represent all possible student enrollments in courses. And then this is what? A practical application of the Cartesian product, in a sense that A and then B is not equal to what? B and then A, because the order matters. Once again, let's take note that what? The order what matters. And so looking at this, the Cartesian product of the set A1, A2 down to A to the base n, denoted by A1, A, denoted by A to the base 1, A to the base 2, down to A to the base n, is a set of what? Of ordered what? N tuples, where n tuples, where what? This n tuples, this, where what? A to the base I belongs to what? A to the set A belongs to what? To the set A to the base I, for I is equal to what? 1, 2, down to infinity. And so this extends the concept to more than what? 2 sets, creating ordered n tuples. And so looking at the example that was stated, which says what? A is equal to what? A contains a set, the element 0 and then 1, and then B contains the element 1 and then 2, while C contains what? The element 0, 1, and then 2. So with this, in working out for this, we are going to pair out what? The 3 of them. So we are going to first of all pick what? 0, pair it with 1, and then pair it with this 0. Because we are picking the element, the first element of A, and then we are pairing with what? All the elements in what? In B and then C. So that is what we see here. And then we are going to do the same thing again. 0 is being paired with what? 0 once again is being paired with what? It's being paired with 1, and then being paired with what? It's being paired with 2. Sorry, it's being paired with 1 and then being paired with what? 1. This one here, sorry, yes. It's this one here. So that is what we see here as well. And then the next one, still on the 0, 0 is being paired with what? This 1 once again, and then it's being paired with what? 2 here, just as we see in this bracket. And now we've now exhausted. Okay, so still on the 0. So we will now pick this 0, and then now we've now exhausted this one here. We've now exhausted this one. So we are now on the 2. So we'll pair this 0 with this 2, and then we come and pair it with 0 once again. Just as I've been seeing here, we're still on the 0 and then the 2. We'll pair it with a 1, and then the next one we'll pair it with a 2. Just as I've been seeing here, and then it goes on and on and on and on to the very last one. And so each possible combination of the elements A, B, and C has now been formed based on the pairings that we did. And yeah, has now been formed based on the pairings that we did. And so let's know that what A and then B is not A by B and then into bracket. So let's know that this is not the same as this. Why? Why? Because the order of operation matters. In this scenario, let's pay attention to the orders, the orders very much, because the order really matters. So this, like I said, this and this, just as captured here, is not the same, because the order of what operation matters in a sense that this one first create what pairs from what A and then B, then pairs those elements with what and then pairs those elements with C, resulting in pairs that contains what pairs as what as a first element. And so what I'm trying to say is that, you see, the reason why this and then this, the reason why this and then this is not the same is because, you see here, there's a parenthesis included here. So when you pick the first element of this, of the A, you are going to pair it with this until you have exhausted all the elements of this, and then until you have exhausted all the elements of A being paired with the element of B. And then when you are done, so when you are done, you now have what? The element of A and B. Now that you come to pair the result of what? Of A and B with C, with element of C, with element of C. And in doing so, it is going to cause a difference in here, because with this, when you pick the element of A, you pair it with the element of B, and then you pair it with the element of C in that order. But here, the difference, the reason why it's not the same is because of the presence of what? Of the parenthesis that is here. And because of the result as well, the result here as well. And so let's take note. Yeah, so that goes what on and on and on. And so want to look at the set. Want to look at the set operations. So in dealing with sets, some of the operations in dealing with sets, yeah, come in. Okay, so just as I was saying, so in dealing with sets, some of the so the union of two sets A and then B is denoted by this symbol here. The symbol, the universal, the symbol here, which looks like a U. That is what the union is, what is denoted by. And so the union of two sets A and B denoted by A union B is a set that is a set that contains the elements that are either in A or what, or in B, or in both. And so like I was saying, so the difference of these two sets, that's set A and then B, is that what? Sorry. So yes, that's what I was saying. A union B has to do with the fact that what A contains the element that are, so all the elements that are in A are also what contained in what in B. Are also contained in B. So that is what the that is what this implies. And so when we look at the example here, you see A, E, O. When we look at the example here in this set, A, E, O, and then union what? I, U, 3. But the union of it is going to be a combination of this set and then this set. It's going to be a combination. Like we are going to, the union has to do with what? The inclusion of all the elements in what? In both sets. That is why we have what? A, E, I, O, U, and then the 3, which is a collection of what? All the elements in both sets. And then same applies to what? The second example here. All right. So all right. So moving on. All right. So moving on. Okay, so having discussed the union operation, we want to look at the next operation, which has to do with the next set operation, which has to do with what? Intersection. So the intersection of two sets is denoted by the N symbol that is noted by the N symbol that is what being seen here. And so A intersection B means that what both sets contains what? A particular element, which means that both sets would contain what? A particular or what? Or a similar, both sets would contain what? A particular same what element. That is what the intersection means. And so what can be found in A, in set A, can also be found what? In set B. And so let's look at the first example here. With the first example here, A, E, O, intersection I, U, 3. See, there is no element of set A that can be found what? In set B. And so the intersection of set A and then set B is what? Is a null set or an empty set. And then with this one, with the second example here, the intersection, because we have 1 and then 1 here, and then we also have 5 and then 5 here, the intersection now becomes what? 1 and then 5. The intersection now becomes what? 1 and then 5. All right. So the next operation we want to look at is what? Is difference. The next operation we want to look at is what? Is a difference of two sets. So the difference of two sets A and B, denoted by A minus B, is a set that contains what? Elements that are in A but not in B. And this means that you take all the elements from set A and remove any elements that are also present in set B. And so the result is a set containing what? Only the elements that are unique to A. And so yes. And so looking at the example here, what this denotes is our So the set of what? All x, such that what? X is an element of what? X is an element of A, and X is an element of A, and X is what? Is not an element of what? Of B. And so this explains what I said with regards to the difference of two sets. That means that what when you take what the element of set A and then remove any element, what any element that also present in set B, the result it should give you is what it should give you a set that contains only the elements that are what that are unique to A. I mean that can only be found in what in A. And so when you look at the difference of this example we see here, so let's look at this example. So the difference of these of set A and then set B is that we are looking for what the set that we're looking for element that are only unique to what to set A. And so because A, E, and then O cannot be found in set B, which is I, E, U, and then 3E, the difference of set A and then B for this becomes what? Every element of what? Of set A, because none of them can be found here. But with this instance, when you are looking for what? The difference of set A and then set B, because we find one and then what? One here, one is cancelled, because we find what? 5 and then 5 also here, both are cancelled. So now the only element of A that is left that cannot be found in set B is 3. And so now our answer for the difference of what? Of set A and then set B becomes what? 3. Just as captured here. All right. And so on the Venn diagram, it will be so on a Venn diagram to find for the difference of a particular set, it will be the portion that is what? That is shaded. The portion that is what? That is shaded that only belongs to what? To the particular set. And so the next operation we want to look at is what? Is a complement. So the complement of set A, denoted by A complement with A having a bar at the top, or with the A apostrophe. Yeah, and so in finding the complement of a particular set, it is known as what? The universal set minus that particular set. So when we are finding for what? The complement of set A, meaning we are looking at the universal set minus what? The set A. Minus what? The set A. And so the complement of a set is always defined relative to what? A universal set. And so just as I said, we find our complement by what? Subtracting the particular set in question from what? From the universal set. And so the universal set U contains all possible elements under consideration in what? In a given context. And then the complement of A consists of what? Of all elements in U that are not in what? In A. And so we want to look at an example. I want to look at this example here. And so what this means is that what means that A complement is equal to what? X is an element. So A complement is basically equal to what? The fact that what? X is an element of the universal set, such that X is not an element of what? Of the set A. X is not an element of what? Of the set A. And so let's look at this example here. Let's look at this example. Let's look at this example that we find here. This example. So this example says that let A be the set of positive integers greater than 10, with universal set as the set of what? Of all possible integers. And so let A, so A become what? A set of what? Of positive integers greater than 10, greater than 10. So we'll begin with 11, 12, 13, and then the likes, and then continuing. And then our universal set in this case contains what? 1, 2, 3. So till infinity and all that. So now to find for the complement of A, to find for what A complement, like I said, it is what? The universal set minus what? Minus the set in question, which is A. And in subtracting all the elements of set A from universal set, you see, the universal set begins from 1, 2, 3, and upwards to infinity. And then the set A consists of element that begins from what? 11, 12, from 11 upwards. Now, when you subtract the element of A from the universal set, because the universal set is comprises of all the numbers which begins from 1 upwards, and then the set A consists of what? Numbers from starting from 11. And I was saying that the complement, when you're looking for a complement, you're looking for figures that are not in A, that are not in what? So you're looking for A complement, you're looking for figures that are not in what? In the A complement, but can be found in what? That are not in A, but can be found in what? In the universal set. And so the only numbers that can be found, that cannot be found in A, but can be found in the universal set, has to do with what? The figures which begins from what? From which begins from what? From U. Which begins from what? 1 to 10. Which begins from what? From 1 to 10. Which begins from 1 to 10. And so our A complement becomes what? 1, 2, 3, down to what? To 10. Because out of the universal set, these are the only figures that will and can never be found in what? In the set A. Right? Okay. So these are some set identities. So that'll be all for the set operations for now. So these are some set identities. Let's read more on this. And so I'm going to skip these ones, and then also these are the continuation. Let's find time and then read more into this. So I'll skip this as well. And then the very last thing that we want to talk about for today has to do with what? Computer representation. The computer representation of what? Of sets. And so with the computer representation of sets, computer representation of sets, let's look at it in two ways. The first one has to do with what? The bit string representation. And so with a bit string representation, the element of a set can be represented in the computer memory using an arbitrary ordering of the element of the finite universal set. And what this means is that we need what? A defined universal set and an agreed upon what? Order for its element. And so let's say a subset A of the universal set can be represented as a bit string of length what? N, where the ith bit in its word will be 1 if A to the base 1 belongs to what? Set belongs to A, and then 0 otherwise. And so each bit in the string corresponds to what? An element in U. And so just as I was saying, so A will be represented as 1 when the so let me use an example here. So let's say we have what? Set A, and then let me use 1. Let me use 1. Let me use 1, 2, and then 3. Let me use 1, 2, and then 3. And then also with that of the, with 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 the Yeah, so with this one, like I was saying, what I was trying to say was that if there's an element that we are looking for that is present in the A, we'll represent it with 1. And so 1 can be found in what? In the set A. So it is being represented as 1. And then 2 can be found in what? Set A. So that will also be represented as 1. 3 can also be found in what? Set A. So that will also be represented as 1. But we mentioned 4 and then 5 because they cannot be found in set A. We represent those ones as what? As 0. 0. So 4 is 0, 5 becomes 0. If should we look for 6? Because 6 is not here, 6 also what? Be identified as what? At 0. So that is what I was trying to see. So let's look at an example. Let's look at an example here. Let's look at an example here. So let u 1 to 10. Let u be equal to what? 1 to 10. So what bit strings represent the subset of all odd? Now let's look at this example. What bit strings represent the subset of all odd integers in u? The subset of all even integers in u, and the subset of all what? Of integers not exceeding 5 in u. Not exceeding 5 in what? In u. And so with this question, we all know, first of all, you have to find what? We are looking for what? Odd numbers. So first of all, you have to find for what the odd numbers are. So the odd numbers, we have 1, 3, we have 5, we have what? 7, and then we have 9. And then they made mention of the fact that subset of even numbers. So even numbers. So the even numbers, because it's within the limit of 10, we have 2, 4, 6, 8, and then what? 10. And then the last thing I was speaking about was that, and then the subset of integers not exceeding 5. So not exceeding 5. That one we know we have what? 1, 2, 3, 4, 5. Not exceeding 5. So meaning less than or equal to 5. So now we haven't stated all our elements that are necessary for the question. Now, like I was saying, in the computer representation, we represent what? An element that can be found in a particular set with 1. And then the ones that are absent, you represent them with 0. That is basically what the computer representation is all about. And so let's take the first one, which has to do with the odd number. So the odd numbers, let's look at this. So the odd numbers. So we have 1 from the odd number. We have 1, which can be found here. So that one be stated here, which is 1. So we don't have the next number. We don't have 2 in the odd number here. So we present it as what? As 0 here. So the next one is 3. And 3 can be found in what? 3 can be found in what? In the universal set, which is here. So it can also be denoted by and then it goes on and on and on and on. So with the second one, the even numbers as well, 1 cannot be found in even numbers, so it is 0. But 2 can be found in the even numbers, so it's also denoted by 1. And then here also, so it goes on and on and on. And then with the last one, not exceeding 5. So meaning the first 5 elements can be found in what? In the universal set, and then can also be found in what? In the set, not in the set containing what element that does not exceed 5. And so that are represented by 1. And then the remaining 5 digits, which is 6, 7, 8, 9, 10, are represented by what? By 0. And so that is simply put what we mean by what? The computer representation of what? Of sets. That is basically the representation of what? Of set. And so let me touch lastly on this. Probably I can take questions and then bring the class to a close. And so the last thing has to do with what? Bitwise Boolean operations. And then with this one, it has to do with what? The union, which is denoted by or the intersection, which is denoted by n. And so to find for what? The union of two sets in the we are still in the context of what of the computer representation. John, kindly hold on. I'm wrapping up. Then you come up with your question. And so with a bitwise Boolean operation, like I was saying, it deals with what the union and then what the intersection. And so with a union, to find for the union of two sets, you perform a bitwise OR operation on their strings. That's if either bit is 1 and then the resulting bit is what is 1. And then also with the intersection, you find what the intersection of two sets. So you perform a bitwise AND operation on their bit. And so only if both bits are 1, and then that is when the resulting bit becomes 1. And so let's look at an example down here so that it doesn't look like I'm speaking mysteries. Let me just break it down with the examples what I'm saying. So with this first example that we see here with the union, let's tackle the union first. With the union, what I was saying that you see it has to do with union. So the first element here, what this means is that whatever is so with a union, what it means is that what a union means is that if either bit is 1, then meaning it has to result in 1. So let's say 1. So you see, let's name this one as what? As set A. And then this one is also what? Set B. This one is also what? Set B. This one is also set B. So when you see 1 here, when you check set B, we also see 1. So automatically it becomes 1 here. And then we see 1 here, and then we see 0 here. But the 1 is because it's a union, we are merging what both cells. We are merging both what sets. And so 1 is meaning, because in union, we know that union has to what we are merging what both cells and both what set. And so one thing you must know is that 1 is greater than 0. And so we, instead of bringing 0, we go with what? 1. We bring the 1 here. But the only instance where we have to bring a 0 is when both instances are 0. So now let's look at this instance. So we have this instance here, and then this instance as well. This instance as well. So both are 0, and because it's union, automatically becomes what? 0. But otherwise, if set A, an element in set A is 1, and then an element in set B is also 0, automatically in the resulting answer, it becomes what? A 1. And so now let's look at the intersection. With the intersection, it's a bit different because both has to be 1 for it to be 1. And then both have to be 0 for it to be 0. And so let's look at this. So in the intersection, both has to be 1 for it to be 1. Else it becomes 0. When one side is 1 and then the other side is 0, automatically it is what? It is 0. This is intersection. And so we pick the first element. We pick the first element here, and then the second element in the set B here. Both are 1, so automatically is 1. But the second element in set A is what? Is 1, and then the second element is what? Is B. We are saying intersection, they have to be equal before it can result in what? In a 1 answer. And so because here is 1 and then here is 0, automatically it becomes what? 0 in the resulting answer. So here what becomes 0 as well. And then it goes on and on and on and on and on. And so yeah, so basically that has to do with what the computer representation of the number set. So of the set of set, yes. So basically that brings us to the end of today's class. So I'll take a few questions and then we wrap up. Yes, John. John, kindly unmute and then speak.
Hello, sir.
Yeah, hello.
Please, you were going too fast. And so when you are teaching, there are some places that some people don't understand. Like me, there were some places that I didn't understand. So you should allow questions, like 2 or 3 people to ask questions whenever you finish a certain slide. Maybe it will solve a lot of people problem. because there was a little understanding I needed, and you said no question. And now, if I'm going to ask all the questions, the rest of my colleagues, they won't get the opportunity to do that. So please, I'm just pleading. Next time, when you are done, then you allow two people to ask questions. Then you answer the questions before you continue. Thank you, sir.
Okay. That's fine. All noted. I'll take that into consideration in our next meeting. All right. Please, any question?
Hello, sir.
Yes.
Please, can you talk about this current slide a little bit?
Can I talk about?
I mean, can you go through this bit, like a bit stream?
The page I'm showing.
Yeah, I mean this current slide.
Okay. So you see, when we're dealing with a set, we got to a point where we had set operations which has to do with the union, and then we did an intersection. We also look for the difference of two sets and all that. And so we are looking at what computer representation of the set. And now we looked at some examples here of how to represent what the set in what in the bits. Yeah, in bits. That's a computer representation. Now when we came here, we're looking at what the computer representation in a case where they are operations, they are operators. And in this instance, we're looking at what the union and then the intersection. And I was saying that the union, you see, in the computer in the bits representation, we deal with zeros and ones. And so I was saying that with a union has to do with what when you have when you say the union of what of set A and then set B, it means you are combining what all the elements of what. It means you are combining what all the elements of what of A and then what and then what and then B. You're combining union has to do with combining what the element of what of A and then what and then set B. And so okay, so we use this question as an example. So it says find the union of what of this figure 1, 3, 1, 2, 3, 4, 5, and then what 1, 3, 1, 3, 5, 7, 9. Find a union. And I was saying that with a union, wherever you find what matching variables, so what I mean is that when you find an element in what in the set A, and then that element is also in what in the universal set, you represent it with what with 1. But if there's an element in the universal set that is not in the set A or set B, it is being represented by what by 0. And so in finding for the union of this set, we first have to what. So we're given what this 1 to 5, and then because 1 to 5 is present in the universal set, so it is being represented by what by 1, and then the remaining, which is 6 to 10, is not found in the set A. So that one is represented by what by 0. So union what? Now the next one, the set B is what? Is 1, 3, 5, 7, 9. And so with that one, we have 1 in the. Is that? Hello, what do you say? All right. So, like I was saying, coming. Good. Okay. So, like I was saying, so when you find an element in what in the set A that is in the universal set, you represent it by what? By 1. And then the ones that are in the universal set, the element that are in the universal set, that cannot be found in the what? In the set A, you represent them by 0. That is why in set A, we have 1 to 5, but here we have 1, we have ones from 1 to the 5, and then the remaining ones are 0 because from 6 to 10 is not found in set A. That is why it's represented by what? By 0. So union what? There's the set B, and then the set B is 1, 3, 5, 7, 9. And so we have 1 in what? In the universal set. We have 1 here, and then 1 is also here. We have 2, but 2 cannot be found in what? In set B. So it is represented by what? By 0. So we have 3. 3 is also seen here. So it's represented by what? By 1, which can be seen here. And then it goes on and on and on and on. And so in combining the two, in uniting the two, wherever you see 1, so with a union, like I said, one of the rules is that wherever you see when you see, because it is union, when you find wherever you see 1, it becomes 1. But when there's an instance of 1 in the set A and then an instance of 0 in the set B, because the 1 supersedes the 0, it is what? It is termed as what? As 1. And so in the addition, let's look at the first 5. Let's look at the first 5 here. So 1 in the union, 1, and then 1 in set A and then set B is 1. So we write it here. And then also the next value is what? Is 1 for set A. So 1 union what? So the next value here is 0. But I'm saying that the 1 supersedes what? The 0 because it is union. So it will still be denoted by 1. But when you are dealing with the intersection, it is only if what? The first element is only if what? The first element has 1 component. If it is 1 and then the other place is 0, it does not hold. But if both are 1, that is when what? It becomes 1. So with what I was saying with the intersection, so with the intersection in this aspect, so let's take the first 2. So 1, 1, and then 1, 0. The reason why it is 0 is not because here, it's not because we are replacing it with this 0. It is because this 0 and then this 1 are not the same. And this one are not the same. This one here, they are not the same. That is why it is 0. Intersection means both sides must be equal. And so we pick the first value, which is 1, and then from the set A and then set B, which are both 1, which is equal. But now the second value, which is 1, is not equal to the second value of set B, which is 0, and so hence it is 0. I believe, and then it goes on and on and on and on. I believe you now get the whole, you now get this particular slide.
Yes, please. Thanks.
All right, then. You're welcome. All right, then.
Yes,
we'll
thank you very much.
You're welcome. So we'll take the next question from Bright.
Good afternoon, sir.
Good afternoon.
Please, this one, since some of my colleagues are complaining in the chat section that they still don't understand this. And I think I have devised a way that I've used to understand. So I don't know if I can share it with them too. I don't know if it's allowed.
Oh, don't worry, feel free. It's
okay.
So
please, before then, I will need you to. I'm talking. Let me begin with the intersection. I would like for you to just. I don't know if you can clear what you've done. I'm talking on the intersection bit.
Okay.
And I want to bring it down to because I've brought it down to my levels. I don't know if I do it that way, they will understand.
Oh yes, it's
okay.
It's a thorough session, so just feel free and then.
Okay, thank you.
Yeah, just feel free. Hope it's okay.
Okay, thank you. It's
okay, yeah, so you can go ahead.
Okay, please. I want my colleagues to think of it this way: that let's say this government, someone comes and says this government has built a school and a church at a particular location. That's the intersection, and for the Boolean gate end or the logic gate, you said the government has built a school and a at a particular location. So note for the first set. Can you please write S at the first set? For the first set on the intersection.
Come again, you said what?
I said I would like for you to write S and the letter S to denote for the first set. Yes.
Where?
The intersection, the bit string, the 111 and the 0. I need you to write
okay.
Yes, and the second one C. Okay. So let's say if someone comes and tells you that the government has built a church and a school, so if you go to the location and you don't find, if you find a church, let's say you represent it as 1, and if you go to that same location and you don't find, I don't know, I don't know how to put it. Let's say if you find a school, you represent it with 1, and if you find a church 2, you also represent it as 1. But
right. Right.
I think his network has break.
Okay.
Please, maybe someone can continue.
No problem.
Yeah.
Yeah, I see another hand.
Okay. Okay, so another. I wanted to explain this.
Who is talking? Is it Prince or Ma?
Yeah, it's me, it's Prince.
Okay, go ahead.
Okay, let me add some contribution to what you were saying
Sure.
about the union and intersection. So for now, when you look at the union and intersection, we can have 1, 2, 3, 4 and 1, 3, 5, 7, 9, where U becomes 1, 2, 3 up to 10. So now here the answer is claimed as union. That is 1, 1, 1, 0, 0, and all those stuff. So for you to use the union, we already said that the union is represented as or we already said that the union is represented as or and and sorry. Hello, please, can you hear me?
Yes, I can hear you.
Okay. The union is represented as O, and the intersection is represented as N. So that O operation means that any of these representations should be true, or else when they are both false, then the answer should be false. So when I pick the first union, when I pick the first one or let's say when I come back to where the S is, I'll pick the first one there. That's the first one. Or then the second one. Have you seen that? When I pick the first one here, yes, I'm coming. Let me indicate it. When I pick this first one and the second one, you could see they are all meeting. That is, they are all meeting. That's for the union. So since we have the first one here and the second one here for the church, that means that they have intersected. So your final answer will be 1. So we want to the next one for the school and the church. We go to the next follow-up number. That is the one. So we pick the one there. We pick the one for the school, and we compare it with that of the 0 there. And I already said that for the union, at least one member of the element should be true, or else when they are both false,
they should be false. So since I've seen 1 0 against a 1 there, that means that your final answer should be 1. Then you move on to the next step of number, that is 1. So when you see the next step of 1 and you compare it to the other one, both of them are 1. So write it as 1. And so you continue that way. But we have to have this in mind that when you are dealing with the or, that is yeah, when you're dealing with the union, at least one member should be true, or else when they are both 0, it should be 0. Please, I don't know whether you are getting me.
Yeah.
Um, uh, since they are both different, that means your outcome should be false, or it should be 0. So that is one intersection, 0 should be 0. That means they don't coincide for that of the n. Please, hope you are getting me.
Yes.
And
Yes.
okay, then move on to the next set of number for the 1. You can see that for the third one, let's compare to that of the third one at the right side. That is so you continuously compare, but bear it in mind that for the when you're indicating, or when you're treating for the intersection, all the parties or all the elements should carry the same value, or else when one carries 1 and the other carries 0, both of them should be false, or you should record them as 0. But for the union, which is represented as all, when one side of the figure carries 1 and at least the other carries 0, it should be 1. I'm sorry, yeah, it should be 1. Please hope you are understanding this.
No. So please, so the one means true.
I'm saying that.
Does it mean that the 1 means true and the 0 means false?
Yes, I guess
that one, listen, that one, it depends on the type of operation that you're dealing with. For the union, that is represented as you. It means that at least one of your observations should be true. That is when you compare the first one, and then you compare the second part of it, and the second part of it is 0 for the I'm talking about the union. When you compare the first one to that of the union of the second one, and you realize that the second one that you are comparing it is 0, I already said that for the union, at least one of the observations should be true. So that is 1 union 0 should be 1.
no.
0. Okay, what's your opinion?
No, you see, for the intersection, 1 union 1 should be 1, and 1
Yes, that's what I'm
union 0
saying.
should be 0.
1 union 0 should be 0.
Yes.
Yes. With the intersection, 1 union 0 is 0.
Should be 0, yes.
1 union 0.
It is the union that 1 intersection 0 is still 1.
Yes.
By the
That's what I'm
intersection.
No.
That's what I'm saying.
1
For the
union
union,
0. Okay,
please
1
listen.
union 1.
Yeah, by that he's on track.
Listen, for the union, I'm talking about the union, not the section.
Okay, not the intersection, right?
Yeah, he was
Yes,
talking
for
about
the
the union.
union.
Okay.
Yeah, for the union, 1 intersection 0 should be 1. Please hope you get it, because for the union, at least one of your observations should be true. But for the intersection, when when one of them, not both of them, for the intersection, when both of them is false, or when one of them is false, the whole outcome should be false. That is for the intersection. But for the union, when both of them are true, and at least one of them is also true, then your whole outcome should be true. Please hope please hope you all get it.
Yes.
Yeah, Prince,
Okay.
you're right.
If you compare this to the truth table, the end gate truth table and the all gate truth table, it will make it easier. So for
Yeah,
those
it
of
will
us
make it
who
very
don't
easier.
understand it, just refer to your truth tables, and it will help a lot.
Exactly.
Yes. Yeah, that's what I can see.
Okay, thank you.
You're welcome.
And sir, please, are you still there? Hello, Mr. Kingsley. Mr. Kingsley.
Yes, I'm here.
Please, I don't. Yes, please. I don't know if I can take you back a little bit. The last but one slide. You were explaining the examples, and you explained the first example, and I was really waiting for you to explain the second one, but you skipped it. Yes. Well, yes. Was it this place? Yes, I think it's this one. Please, you explained this one, but the second one, I really wanted you to explain this one.
Yeah, because this example is nothing as compared to the first one. If you have the knowledge about the first one, you should be able to solve the second one, because it is talking about the union of what is the bit string for the complement of the set of all odd numbers. So you know that all odd numbers, we have 1, we have 3, you have 5, you have 7,
And
and then
9.
you have 9.
Yes.
That is the odd numbers. And then, you know, because we are dealing with the universal set of 10, that is why we are ending at 9. And to, you know this, and now they're asking you that find a complement. What is the base string for the complement of the set of all odd numbers? So, and what you need to know is that when you're finding for a complement, it's going to be what? The universal set minus what? The A. Coming. It's going to be what? The universal set minus the A.
Okay.
So minus the A, what are we going to get? We are looking for what? Things that we'll see in the universal set that we'll not find in what? Things that we'll see in the universal set that we'll not find in the A. And to what is left aside 1, 3, 5, 7. So we now have 2. So we are just going to be left with just even numbers. We have 2, 4, 6,
8.
we have 8, and then what? 10.
Yes.
And then the 10. So that is all we have. So now when we have 10, so we now have 2, 4, 6, 8, 10. Now we are going to convert this. We are going to look at the universal set. We are going to use this to compare what? The universal set, and then we now convert it into what? Into the bit string, the zeros and ones. So in the universal set, we have 1 here, but we don't have 1 in the A complement. This is A complement.
I mean, it's okay. Yeah.
Sorry, my network went off. So like I was saying, where we ended at, so like I was saying, when you subtract what? The A from the universal set, what you are left with, it becomes what? The A complement. And so we are going to compare the A complement to the element of A complement to the universal set, the element of what? Of the universal set, and then you strike out what's the difference. So like I was saying, we see 1 in the universal set, but we don't see 1 in the A complement, so it becomes automatically what? 0. Now we have 1 in the universal set. We have we have 2 in the universal set. We have 2 in the A complement. So it's being represented by what? By 1. And then we have 3 in the universal set, but we don't have 3 in the A complement. So automatically that one is 0. So now we have 4. 4 is in the A complement. So it will also be represented here as 1. And so on and so on. Do you get it now?
Yes, sir. Thank you very much. Thank you for the explanation.
Yes, sir.
You're welcome. So basically that should be it. Yes. So I believe that should be all for today.
Okay.
Next week,
Okay.
same time. Today, so sorry for the delay. So sorry for the delay in starting the meeting, but next week we're going to start early. So same time next week, Wednesday, 11:30 a.m. Okay. So God willing, we'll meet next week, Wednesday. Have a wonderful day.
Thank you. Thank you.
Thank you so much. Bye.
We'll make it.
Welcome.
Thank you.
You're welcome.
Vida,
Yes, Nico.
yeah, I saw you recording, so please, when you are done, forward it inside the group. Man.
How do you know that I'm recording?
Nico is always giving you close marking.
Once they see me in the group, now they know that I'm recording.
He's always giving you close marking. Don't mind him.
You buy data for that. Bye bye.
Don't worry.